This time we are discuss about the PN junction. Last week we learned about the two kinds of doping. First, it is N-type doping, and second is P-type doping. The difference is that in N-type doping, we are using 5 groups such as prosporone, so the fermion level goes up and the gap between the conduction band and fermion level is narrowing. The P-type case, we usually use 3 groups such as boron. So if we dope the boron, the fermion level goes down, so the valence band and the fermion level gaps is narrowing. But if we combine this N-type and P-type semiconductor, we can draw it like this. It means the PN junction. The P-type semiconductor and N-type semiconductors are combined, and by combining this, the gap made it, and by this gap we will control the current flow. Then first we have to discuss about how to draw the PN junction. So we have to know how to draw the energy band diagram of PN junction. So we have to discuss about the equilibrium state. It means the thermal equilibrium. In this case, the N-type and P-type fermion levels are constant. So first we draw the fermion levels constantly, and rewrite the conduction band and valence band, and be aware that we have to keep the gap between conduction band to fermion level and fermion level to valence band. So draw like this. This is N-type region, and there is P-type region. After that, just combine it. By this step, we can draw the PN junction in thermal equilibrium state. Then we also know that in N-type case, the valence band to conduction band to fermion level is more narrow than the fermion level to balance band in p-type. So we also know that the n-type doped is more than p-type. And also, in p-type junction, we can see the depletion region. It also said SCR is space charge region. I will draw the PN junction like this. And the n-type doping is 2 times more than p-type. So I will draw like this. Then we can draw like this. Why I draw this in n-type case, why I use the plus, and p-type case, why I draw the minus is the n-type donor gives electron. So by giving the electron, the donor is ionization. So the donor ion keeps the plus state, and p acceptor case, by receiving the electron, so the acceptor is ionization and they keep the minus state. So I draw it like this. And this state is equivalent state. But the p-type and n-type junction, and they combined like this. Combined and combined. So the depletion region makes more like this. So if the more doped, the depletion region is narrowing. So the less doped region, less doped part, the depletion region is more wider. So in PN junction, we can use by giving some bias, so we can control the current flow. So let's we see the 3 states. First is equilibrium state, and second is forward bias state, third is reverse bias state. First case is an observer equilibrium state. It just have 3 kinds of current flow. First is generation and recombination, and just diffusion current. First, generation and recombination is similar that last time we learned about the EHP. So the electron or hole, the electron of the valence band goes up to the conduction band, and after a few times, the electron goes down again to the valence band. By this movement, the generation current and recombination current are appeared, and theirs are same current, so it doesn't have any specific current flow for p-n junction. And third is diffusion current. It's from the difference of the doping states. So, but the equilibrium state, it can't have a much diffusion current because it has this barrier. We call that built-in potential. So by this barrier, the electron can't go from the other type, so it doesn't have much current. It only flows a little current. But if we take a bias for this p-n junction, this barrier gap is narrowing. This barrier goes down, so we can see this flow, current flow, more a lot. So by this difference from the n-type and p-type doping state, the diffusion current flow exists. We can call this forward bias. So if we get more forward bias to p-n junction, the different current goes up exponentially. The last is reverse bias state. In this case, there is n-type and there is p-type. So we combine the bias and n-type to plus, p-type to minus bias. So the barrier is more and more, so the current doesn't flow like this. The electron makes a barrier, so it can't go broad to another p-type region. But so as a result, it doesn't make a current flow. But if we get too much reverse bias to p-n junction, in this depletion region, the band gap is narrow and narrowing. So by this narrow band gap reason, the electron just go to the another region, and the tunneling effect exists. So by this tunneling current, the current flows if the reverse bias is too large. So we can draw this IV curve. The y-axis is I and x-axis is V. So this position is forward bias and this state is reverse bias. So as I explained, in the first forward bias state, if we get the more bias, the current flows exponentially. But the reverse bias state, it doesn't have any current flow, but if the reverse bias goes larger and larger, suddenly the current flows like this. So we can draw the IV curve like this, but the more exactly draw the IV curve, we can draw like this. I exaggerated this y-axis and this reverse, even if we get a reverse bias, there has a leakage current, but it is too small, so we don't have to consider about this current. So I said I exaggerated this y-axis. So this time we discussed about the p-n junction.